a long distance, like those that I'm measuring are about 80 million light years away sometimes. So it's a huge distance, and that's why, is this clear about the standard candles and stuff? You know what is the redshift? Or shall I explain redshift and... Well, redshift is just more or less Doppler effect, as something is where the observer, and if something is receding from us, going in that direction, the light that is emitted goes stretched. If we were looking here, it would seem to be squashed. And because this one is much shorter wavelength, is bluer, longer wavelength is red, and that's why we call it redshift. Because all the wavelengths, all the discrete wavelengths that it has been emitted, it has emitted, are stretched, so that when you take the spectrum, like lambda, you would expect to see different lines of emission. For instance, the famous 21 centimeter line, which is the Lyman alpha limit. You would expect to see it at a given position because you know exactly what is the transition in hydrogen. But then you see that it has moved here, and you are sure that this is the line. So it immediately tells you what is your redshift. And that's why it is called redshift, purely because it is the transition to a redder part of the spectrum. There is also accordingly blue shift, as I say, if we are here. But this is not the cosmological blue shift, but rather a local blue shift. Because cosmologically, it happens on a large scale. It's not obvious to understand it, so I think it's just useful to think about it, that our galaxy is in the cluster of other galaxies. I mean, here we've got Andromeda, some other galaxies, some ellipticals as well. And this is like a cluster of galaxies. So these galaxies are all together moving in a system, so that they would have some peculiar velocities. They would be attracted by the members of the group. Just like stars in our galaxy, you don't see redshift in the stars because the gravitation of the system is much bigger locally than the expansion of the universe. But on a large scale, this cluster from another cluster is getting away. So this cluster is receding. The distance is increasing. So even though a galaxy, one of those galaxies might appear to be moving towards us, for instance, the famous example is Andromeda, which is going to hit our galaxy in about 10 billion years. On the large scale, all of those are receding because the recession speed is much bigger than all those smaller peculiar movements, so-called, inside the group of the galaxies. And that's why it's important to think about it when you have got this that velocity of receding is some constant times radius, and then you see a supernova in one of those galaxies, and you measure the distance, it gives you R. But you have already measured R because you know V. So this enables you to get the Hubble constant. H0 is basically the velocity that you measured from the redshift divided by distance. And that's how nowadays we are getting H0. Nowadays we are getting H0 by observing a lot of galaxies in a given region. Sometimes we take some smaller cluster where you can detect Cepheids as well. So you observe Cepheids, you observe supernovae, and you measure the redshift. And all these things together combined give you an estimate of velocity and the distance, and this enables you to get the Hubble constant. And Hubble constant is so important because it is fundamental in the Einstein field equations Friedmann equations and anything that describes the cosmology of large-scale structure of the universe. I mean, the most famous one is just Friedmann equation, which is A dot over A. I will tell you in a minute what is A dot over A, but this is actually H squared. Is 8 pi g rho over 3. Is there a c squared as well? I don't think so. Minus some curvature term plus a cosmological constant. And this describes the evolution of large scale of the universe, because A is a scale factor. A at the beginning was not. At the moment, it's now. It's 1. And A tells you how much the universe overall has expanded since the Big Bang. So we can, for instance, say that when the universe was 300,000 years old, A was 1,000 of our current A naught. And A dot tells you how quickly it is expanding. And that's called also the Hubble flow, because galaxies are in the Hubble flow as if you had a fluid which is flowing strangely in all directions away, and galaxies are just embedded in that flow. And locally, gravitationally, they can move around, but on the large scale, they have to follow the flow. It's just like being in the river and trying to play with your friends in some kind of swimming water volleyball. Or you can throw the ball to each of them and you can try to get closer to them, but you're not going to be able to swim against the river because it's so quick. And it's exactly the same with the Hubble flow. And H is fundamental parameter. You can rewrite that equation into this form. And these omegas are just different contributions to the density. Omega in total has to be 1, but it's composed of four. Omega radiation, matter, curvature, and lambda. And all those parameters evolve differently with A, so that this one, for instance, is very important at early times. So this will be contribution to total omega, and this will be A. Then the matter would evolve slightly less violently, then curvature has got smaller dependence with A. This can be omega, it will be H. And then you're getting lambda, which is constant. And that's why we say now that we are in this region, which is dominated by a constant. By a constant, which is a cosmological constant, which is very clearly connected to Hubble constant. And that's why measuring supernovae and knowing all that about the evolutionary history of galaxies, of stars and galaxies is important, because this gives you an understanding of how the universe is expanding and how quickly is it expanding, and like what is the connection between different components of the universe. So I'm not sure if you are bored, or would you like to hear about data acquisition? How does the telescope work? Just tell me if you want me to stop, or do you want me to continue, or ask questions.
How does it connect to dark energy?
Oh, dark energy. Very easily, actually. With supernovae, for instance, you know what are the movements of those galaxies in the cluster? So they appear to be moving much quicker towards each other than the visible matter that we have. and you've got. They appear to be bound much more.
At what?
The galaxies. Than as if there was just a visible matter. And that's why when you see a cluster of galaxies, when you like detect gas, then you know that the cluster of galaxies is actually mostly gas. And mass of cluster is 10 times the mass of gas in dark matter plus the mass of gas plus 1/10 of mass of gas, which is stars. So stars are only 1% of what we see in the as the mass of the system, and we know the total mass by the gravitational interaction, because we know how the galaxies move around and also how the galaxies are bound, because the stars around the core of the galaxies do not go like planets, say, in the solar system. Planets in the solar system obey Titus-Bode relation, which is an empirical relation connecting the period and the distance. But they are Keplerian, so that the further it is, the slower it goes. But counterintuitively, when you take stars in a galaxy, like our galaxies, and you take velocity versus radius, and you plot them, you've got obviously the core, which doesn't go much around itself, but then it stays flat. How could it stay flat if they're just further away? So they should be revolving much slower. It should go like that if it was going to be Keplerian. So because of the fact that those curves are not flat, we know that there has to be much more dark matter. There has to be much more matter which we can't see, and that's what we attribute for dark matter. But you were asking, how does it connect to Hubble constant? I've just told you two proofs why we know that there is dark matter. But then dark matter is connected to Hubble constant by the fact that this omega, when I told you it's omega matter plus omega radiation plus omega curvature plus omega lambda, we are not sure. But it seems that when you Google it on the internet, it's gonna give you a lot of different answers. But people would agree that about 1% of omega is visible matter, baryonic matter. So stars, galaxies, dust, everything. That's just 1%. About 30% of that they attribute to omega lambda. And then this omega m would have to be combined of both dark matter and matter. But matter is just 1% of everything. And we know that this is the value of that omega because of the expansion measure. We measure how quickly it is expanding. If you had a bigger omega, it would be expanding much slower. If different parts of those omegas, like omega k or omega lambda, had different value, you would have a different contribution of all those different omegas to h, which is the expansion. So you measure the expansion of the universe at different time because you observe galaxies at different redshift. Very far away galaxies are observed roughly at the beginning, when we can see galaxies which have formed just a few million years after the Big Bang. So they are the very first galaxies. And we observe what is their redshift, what is their property, how many galaxies have been there at this moment of the universe, what is their spatial distribution, and this tells you about the content of the energy overall in the large-scale structure of the universe. And then you plug it into the numerical models, and the numerical models are trying to predict exactly the same composition, and they do. This is the nicest thing about all those, yeah?
So we're talking about that dark matter, right? Ask about dark energy. So from the graph, it seems that the Hubble constant is constant.
Yeah,
But they say that universe accelerates its expansion.
Mm-hmm.
So is it that there's some other term that's actually that's linear in H? Is in A? Sorry.
They don't know what is dark matter. They don't also don't know what is dark energy. So it's just calling the unknown in a different way.
So this thing that you drew doesn't include that.
No,
There must be something else.
it must be something else, yeah. So dark matter, dark energy. I call it collectively because they don't know what is either. So it's just a measure of ignorance, really. We don't know what is 99% of the universe composed of. So we choose to call 1/3 of that the energy and 2/3 dark matter. I guess that cosmologists would argue that dark energy would interact differently than dark matter. So dark energy would just create the pressure, whereas the matter would interact gravitationally. So that the energy would be trying to push the universe against, whereas the matter would be trying to squeeze the universe back. And I guess this is why they need the different ratio of energy to matter, so that you would be able to have the expansion of the universe at the rate that we can see it. But whatever is, this is why you have got this 1/3 of dark energy and then 2/3 of dark matter, because matter is trying gravitationally. Dark matter, we believe, acts just like normal matter when it comes to gravity. That's why we believe that this is why the curve of rotation looks like that, because we basically believe that there is a galaxy, and then there is a huge halo of dark matter around it. And that's basically what pulls all those stars and forces them to hold steadily. And this is roughly 220 kilometers per second in our galaxy. That's roughly where our sun is. So every single galaxy, including ours, is affected by dark matter. There's a lot of dark matter. And it does interact gravitationally, but because it doesn't in any other way, at least as far as the theory is concerned, we have never observed it yet. But people are trying to make measurements to, like, the particle physicists especially, are trying to devise experiments which would be able to measure the existence of dark matter. Because it should show up at some energy level. I mean in the particle accelerators in CERN, for instance. And this is the dark matter which just tries to keep everything together gravitationally. Dark energy would be just the energy contribution to the vacuum. And energy would be just adding the energy to the system. It's just like with the sun, with the orbit. Like when you've got the orbit around if you've got like the potential, that's standard potential radius. If you've got that amount of energy, it's unbound. If you've got that amount of energy, it's circular, like the orbit around. If you've got that energy, it's going to be elliptical. If your energy is 0, then it's going to be paraboloidal, and if it's more than 0, it's hyperbolical, so it's unbound. So this was just the energy of this was just the potential well of around one body, and then I was talking about another body. As it comes along from infinity, it's going to get a bound or unbound orbit. And I guess it's kind of similar when you think of the energy contribution to the universe. If you get more energy, it's less bound. If you got less energy, it's going to be less bound. Still, it's interesting. Do you want to hear about the telescope at all? Because I guess we've already had 1 hour, so I don't want to keep you. I can show you quite quickly how does the telescope work. And this was just one of many pictures of different supernovae that, as it exploded, it has ejected a lot of material into the surrounding system. And before, like in all the stages of the evolution, and as it exploded, the gas of explosion hits the material that has been ejected before, and this is what creates those rings. These are just shock waves going through the system. And because the explosion is 3D, you've got also a ring there and a ring there. And that's what the supernova 1987 looks like. Actually, the first thing that we detected was not light, but neutrinos. Wait, first was light, then neutrinos, 2 weeks after that. And that's like
Really?
yeah.
Was it the other way around?
Well, neutrinos shouldn't be the first one because they do not travel quicker than light. That's the biggest proof that neutrinos are not faster than light, because for supernova 1987A, we first saw the light and then we detected neutrinos 2 weeks after that. It wasn't the other way around, and I told you where do the neutrinos come from. The neutrinos actually drive the explosion. So WETON has got telescope CCD user interface. I've showed you a bit of user interface, it's just a computer program. And when it comes to observation, it's a lot of technicalities. You just have to like take flat fields, dark fields to account for hot pixels on the CCD, flat field to account for different curvature of the detector, and then you need to divide by flat, subtract dark. It's just the processing the image. And I mean, the interesting thing is calibration, because you have to calibrate everything. You don't know what is the brightness of the thing that you measure. You only know what is the flux, the count of pixels. You would have the count of 200,000 photons on a given pixel. But what is the luminosity of that? You don't know. So you have to take an image of the photometric star on a good night and measure that this star, which we know what is the magnitude of that star, gives us that flux. And then we scale all our measurements, because otherwise my pictures are useless.
How do you know the luminosity of the star if not observing?
Because it's standard.
We choose it to be standard.
It's standard in a way that we just measured the brightness in a different way. So, for instance, you might know the size of that star and the distance. So the measure of brightness tells you the distance. For supernova, we don't know the distance; we only measure the brightness. So basically, you could have a nearby star for which you measure the parallax and you measure the brightness. And by measuring this flux of photons and distance and knowing what type of star it is, so you know the surface temperature, you know sigma T to the 4, so you know what's the luminosity. And depending on how much photons you detect, you scale your system. Does that make sense? Yeah. And in the same way, using this known star, I have to scale my system.